Alright, hello again. I'm Matt Russell, as you probably know by now. And today, in this video I should say, we're going to go through the strong form of the Shumlak-Hartman criterion as applied to a Bennett vortex. So the great thing about this is that we don't have to do all that algebra again that we did in the last video, because it was general. We didn't say anything about what T was. In this video, we're going to do something different. In this video, we're going to say that T is a power law. I should be writing the other side here. T is a power law. Okay? That means it's some proportional factor times r to the n, where n is an integer. Okay? Now, what is this CT? We've actually already done this before in the second video. And so we know that it's just the edge plasma temperature over the pinch radius to the nth power. And this just comes from our boundary condition, right? Here's our core boundary condition in this look, right? And here is our edge boundary condition, okay? Now, you can see here that chi-squared, again, we're going back to that chi-squared because it's very important. And it's dependent on r now. So when we do all this math, when we plug in this power law temperature into here, what we see is at the end, we get this parameter out called CDT. And this is an extremely important value because this value sets a lot. It decides where the shear layer is going to be located, because these structures, they go from 0 to 100, not immediately, but over a pretty small distance. It all depends on this guy. This guy is related to where the maximum shear is located. So, again, we can just pick up where we left off. And where we left off is right here. 2t, t prime r. This is from the last video. It's got to be greater than 0. The question we want to answer is, what does n need to be? Okay, all we got to do is take a t prime. That's easy. So this implies that we have t prime r minus 2t greater than 0. Therefore, we have let's just take this derivative real fast. We have n ct to the n r to the n minus 1 times r. That's very important. And this implies that n, okay, this is not 0. This value cannot be 0. The only way that this is 0 is if the pinch radius is infinite, which is very interesting. That's actually something that I hadn't realized before. And I think that what that implies is that if these pinches get too large, the shear properties will collapse. Anyways, what we find is that n times r to the n is greater than 2r to the n. But these just cancel. Therefore, the strong form of the Shumlak-Hartman shear-flow criterion is n greater than 2. Now this is a strict inequality, strict inequality, right? But what's interesting is that if n is equal to 2, well, then we have a parabola, and we saw that previously the weak form admits t greater than r squared. So it's a very interesting connection there. And what's most interesting about this is, of course, that it's suggestive. It suggests what we should check for n, which is n equals 3. that is the case we're going to check in our next video, right? And we'll call this the minimum energy state? Question mark? Anyways, this has been a short video, and I think that's good. So I'm going to stop it here because we got our result that n is greater than 2, i.e. that this thermodynamic gradient needs to be enhanced for this profile to be shear flow stabilized. And I'll also make another note, two other notes real quick before I end this video, is that one, we still have to calculate the magnetic field. And if the magnetic field goes to infinity, the game is lost. Because that was one assumption we made in getting here, is that B does not go to infinity. The other thing I want to say is, to whoever liked the video, the second video, you have no idea how much that meant to me, how grateful I am to have your support. It means everything. I'm an independent researcher. I'm just a guy that came up with a problem at the last hour to stump ChatGPT and Gemini to make ends meet. I wasn't even thinking about any of this. This all happened in the months after. So with that said, this is YouTube, so please feel free to like and subscribe, and I will see you all next time. Next time, we will begin by investigating the n=3 case, and we will look at what the flow profile becomes and see if we can figure out what the magnetic field is. Thank you.